Hello everyone, my name is Zach and I'm a physical geographer, geomorphologist, and educator. Welcome to Bite-Sized Geomorphology, a series of short lectures designed to teach introductory topics in the field of geomorphology and physical geography. In this short lecture, we're going to be talking about grain sizes in fluvial systems and touch on some of the basic aspects of sediment transport. So let's dive in. Sediment, quite literally, comes in all shapes and sizes. As we see this picture on the right-hand side, that is my hand, just to give you some scale. And those are grains from a beach in Southern California, just kind of highlighting the massive variation in grains. We typically describe sediment by its composition, such as quartz or feldspars, for example, but in this case, we can see these large boulders are all different colors, signifying different mineral compositions. We also describe it by its shape, which ranges from very angular to well-rounded. Now, this point bar on the banks of the Little Missouri River in North Dakota in the United States, it's a little tough to see from the scale of the image here, but there are a vast array of different shaped gravels and sands. And then finally, its size, which ranges from boulders to clays. We can see here there are grains that are nearly invisible to the human eye. And then we see these much larger pebbles and cobbles strewn throughout. Now, we're not going to be really talking much about composition in this video, but we are going to be focusing on shapes and sizes of grains. So let's switch over to shapes. So grain shape, we can see here, ranges from low to high sphericity and from very angular to very or well-rounded. This graphic was adopted and modified from Miller and Henderson 2010. These example grains give us insight into the different shapes that grains can take, from angular, which features heavily fractured, sharp-edged grains that might be the result of grain-to-grain impacts, to well-rounded, which typically suggests prolonged transport in a stream or by the wind. The rounding process typically occurs as grains tumble downstream or downwind, and edges of the grains impact other grains, crushing the edges and smoothing the grain out. Sphericity, which ranges from low to high, is another metric used to describe shape and can be considered as a relative proxy for how long a grain has been tumbling about in a system. However, it should be noted that this is not a perfect concept and that there are many different drivers of sphericity that we won't really dive into here. Grain size is much easier to characterize, as it's binned into distinct groups. Boulders, the largest group, occupy sizes greater than 256 millimeters. Gravels occupy between 2 and 256 millimeters. Sand, 6/100ths to 2 millimeters. Silts from 2/1000ths to 6/100ths of a millimeter. And clays below 2/1000ths of a millimeter. The bins presented here are coarsened, as, for example, gravels are often split into cobbles and pebbles, and sand, silts, and clays can be split into very coarse to very fine fractions as well. Now that we've talked about what grains are shaped like and how they range in size, we're going to move into why these factors matter when we consider how a single grain of sediment begins to move. Let's start this new section by touching on a couple of key concepts. Now, first off, we'll briefly define a threshold and its context in geomorphology. Now, a threshold refers to a transition within a system brought about by an internal or external variable. For example, when a grain changes from being at rest to moving because the velocity variable has increased, a threshold's been crossed and the state of the grain has changed. In this figure on the right from Shum 1979, Shum plotted the increase in the slope of an alluvial fan head, which we would also call the apex of a fan, against time. In this example, as the fan head slope increases above a certain slope value, or a threshold value in this case, shown by the dotted line, incision will occur and the fan will trench. And we see that a couple of times cyclically in this graph here. Now, with grains of sediment, this threshold concept is similar, but the forces at play, pun intended, are different. The primary variables we are concerned with here to initiate the motion of grains are different components of force. If we remember back to our introductory textbooks, force equals m, or mass times acceleration, or abbreviated often as F equals ma. The primary forces we're concerned with here are the forces of gravity, F sub g, the lift force, F sub L, and the drag force, F sub d. Now, if the forces of gravity are stronger than those of lift, then the grain stays at rest. However, if the forces of lift and drag are stronger, then motion will start. Now let's finally bring this all home to grains. Here we can see a log-log plot with mean flow velocity on the y-axis and particle size on the x-axis. This handy plot is called a Hjulström curve and was originally published back in 1935. Here we can take our grain size and flow, cross them, and see if we are transporting grains, entraining them, depositing them, or eroding them. For example, say we were to have a sand grain that is 0.5 millimeter in size, plotted right here, and a flow velocity of 10 centimeters per second, plotted right here. We would have a grain that is in transport, but not entrainment, right here. However, if we were to increase that grain size to, say, 10 millimeters, we would not have transport, and other 10 millimeter grains would likely be depositing if they had been previously entrained and transported in flow. And finally, if we were to go back and increase, for example, the speed of flow and keep the grain size constant, we would see that we would exceed the threshold to entrain grains and would even be eroding more than we were depositing. Now, we may notice that it is a little bit tougher to entrain smaller particle sizes like clays and silts. This is because such grain sizes are usually fully encompassed by something we call the laminar sublayer. Now, we're not really going to get into that here as it's a much more complex topic, but there are also other factors such as cohesive forces between grains of this size that make it a lot more difficult to overcome the forces of gravity and entrain the grains. Now, before I recap what we've talked about today, I'd like to note that we are really only touching on the basic concepts here regarding the initiation of motion. In reality, it is an incredibly complex and ever-improving field. And as I typically do, I'll suggest some papers for the interested reader. The top paper, Geomorphic Thresholds, the Concept and Its Applications by Stanley Shum, 1979, dives into the concept of geomorphic thresholds and how geomorphic systems are impacted when these thresholds are crossed, much like we talked about today. The second paper, Resistance is Not Futile, Grain Resistance Controls on Observed Critical Shields Stress Variations by Elwin Jaeger and others from 2018, is not for the faint of heart. It is a phenomenal paper that decomposes many concepts related to the initiation of motion that we didn't get to touch on in this introductory video, but it is geared towards the expert. So if you're going to dive in, make sure that you have a good math background or a friend who can help. So today, we talked about the different bins of grain size and shape, and the concepts of geomorphic thresholds, how they relate to the initiation of motion, and finally how grain size and transport all tie together as modeled by the Hjulström curve. As always, I've provided links or citations to all reference materials in the description below the video. I hope you enjoyed the video, and I hope you have a wonderful day. Thank you.